Today, AI isn't just analyzing data, it's stepping into the lab, designing molecules. That could become the next breakthrough drug, material, or chemical solution. In this video, we'll explore exactly how you can use these tools to create molecules that were once the stuff of imagination. AI-powered molecular design. Artificial intelligence has moved beyond simple data analysis to actively designing molecules with specific properties. These tools leverage machine learning algorithms to predict chemical interactions, optimize molecular structures, and even propose entirely new compounds. Traditionally, creating a molecule with desired properties required months or even years of trial and error in a lab. AI now dramatically shortens this cycle by computationally generating candidates, analyzing their potential activity, and suggesting modifications that improve efficacy or stability. Modern AI systems rely heavily on large data sets of chemical structures, biological activities, and reaction outcomes. By training on these data sets, the models learn to recognize patterns that would take humans decades to identify. This predictive capability allows chemists to focus their experiments on the most promising compounds, rather than testing every possible variation in the lab. Generative models and molecule discovery. Generative models, particularly those based on neural networks, such as Variational Autoencoders and Generative Adversarial Networks, have become central to AI-driven molecular design. These models are trained to generate new molecular structures that conform to desired chemical properties. By encoding molecules into a latent space, the AI can manipulate molecular features, combine motifs from multiple compounds, and output novel structures that are chemically valid and potentially bioactive. In practical applications, researchers can specify constraints such as solubility, stability, or target binding affinity, and the AI will propose candidates that meet these criteria. This capability transforms the molecule discovery process, especially for pharmaceuticals, agrochemicals, and material science. Instead of relying on intuition or historical data alone, scientists now have a virtual assistant capable of generating hundreds of viable compounds in the time it previously took to synthesize a single molecule. Predictive modeling for property optimization. AI does not only generate new molecules, it can also predict their chemical and physical properties with high accuracy. Machine learning models such as random forests, gradient boosting machines, and deep neural networks can estimate solubility, permeability, metabolic stability, and binding affinity from molecular structure alone. These predictive models guide chemists in selecting candidates with the highest likelihood of success before any lab work begins. The integration of predictive modeling into molecular design enables optimization loops where generated molecules are evaluated in silico, refined, and re-evaluated repeatedly. Open source tools democratizing chemistry. Several free open source platforms are now available that allow researchers, educators, and even hobbyists to explore AI-driven molecular design. Tools like RDKit, DeepChem, and OpenMolCast provide environments for molecular modeling, property prediction, and AI-driven optimization. These platforms combine cheminformatics capabilities with machine learning frameworks, making it easier to build and test molecular generation pipelines without the need for expensive proprietary software. RDKit, for instance, is a widely used toolkit for cheminformatics that allows users to compute molecular descriptors, simulate chemical reactions, and manipulate structures programmatically. When paired with machine learning frameworks like TensorFlow or PyTorch, RDKit can serve as the backbone for generative models and predictive simulations. Similarly, DeepChem provides pre-built models for molecular property prediction and reinforcement learning-based molecular generation, enabling users to experiment with AI-driven chemistry workflows, even with minimal coding experience. Reinforcement learning for targeted molecules. Reinforcement learning is another technique increasingly applied to molecule design. In this context, the AI acts as an agent that navigates chemical space, receiving rewards based on how well candidate molecules meet predefined objectives. The advantage of RL in chemistry is its flexibility. Objectives can be highly complex and multidimensional, incorporating both experimental constraints and theoretical predictions. This approach allows scientists to explore regions of chemical space that are unlikely to be discovered through traditional methods or random screening. Integration with experimental feedback. AI-driven molecule design is most powerful when coupled with real-world experimental data, high-throughput screening, automated synthesis, and rapid analytical techniques provide feedback to the AI models, improving their accuracy and relevance. Closed-loop systems, where AI proposes molecules, experiments test them, and results are fed back into the AI, create a continuous cycle of learning and refinement. This approach is increasingly referred to as self-driving labs and is changing the way chemistry research is conducted. The feedback loop also allows AI models to correct for biases in training data, which is critical in molecular design. AI in drug repurposing. One of the most exciting applications of AI molecular design is drug repurposing. By predicting how existing compounds might interact with new biological targets, AI can identify candidates for treating diseases they were not originally designed for. This approach has been especially valuable in urgent situations, such as pandemic response, where time is critical. AI can quickly sift through thousands of approved drugs and propose those with the highest likelihood of effectiveness against a novel pathogen or disease pathway. Beyond repurposing, AI models can also suggest minor modifications to existing drugs to enhance their potency, reduce side effects, or improve pharmacokinetic properties. Challenges and limitations. Despite its promise, AI-driven molecular design is not without challenges. One major limitation is the quality and completeness of training data. Machine learning models can only make reliable predictions if they are trained on datasets that accurately represent the diversity of chemical space. Missing or biased data can lead to false positives or overlook potentially valuable molecules. Collaboration between AI and chemists. AI is becoming a collaborative partner rather than a replacement for human chemists. It excels at exploring vast chemical spaces, predicting properties, and optimizing structures quickly. But human expertise is essential for contextualizing results, designing meaningful objectives, and interpreting complex biological implications. The combination of AI efficiency and human intuition is redefining molecular discovery, making it faster, more targeted, and more innovative than ever before. Looking forward, the integration of AI with quantum computing, advanced robotics, and multi-omics data promises to further accelerate molecular design. AI systems capable of reasoning across chemical, biological, and material domains could one day propose molecules that simultaneously satisfy multiple complex constraints, from efficacy to sustainability. If you're fascinated by the future of science and want to see more ways AI is reshaping research, make sure you hit that like button. Don't forget to subscribe and turn on notifications so you never miss a video.